All right, today we are going to begin looking at our next set of parent graphs, and that are exponential graphs. So in this unit, we're going to be studying both exponential and logarithmic functions. So today we're just going to look at the exponential graphs and what they look like and what the effects of different parts of the general function have on the parent graph. So we should probably know what an exponential function is in order to be able to see what the parent graph does. So an exponential function involves the expression b to the x, where the base b is a number greater than 0. So it could be a fraction, it could be a whole number, but either way it's bigger than 0. If b is greater than 1, we call those exponential growth, and we'll study those a little bit more in our next section. If b is between 0 and 1, meaning a fraction that's less than 1, we call those exponential decay. We have a new vocabulary word here, and this is going to be very important because several different types of parent graphs that we're going to study this semester have these. And that vocabulary word is hard to spell. This is what it looks like. We read that asymptote. So asymptote is a line that a graph approaches as you move away from the origin. So as x approaches infinity, as x approaches negative infinity, if the graph is getting closer and closer and closer to a specific line, then we call that an asymptote. We're going to explore the graphs of exponential functions, and to do this we have to look at the general form. So just like for parabolas, we looked at the general form that looked like this. And for absolute values, it was virtually the same thing. It looked like this. We just did square and cube roots. Now we have the same idea for exponential functions. And here is our general form. So it's a times b raised to the x minus h plus k. Notice that the x and the h are both in the exponent. That's why these are called exponentials, because the variable is in the exponent. So our goal is to determine how each of these variables in that formula affects the graph. So we've got a, we've got h, we've got k, and then of course we have b. So hopefully we've done so many parent graphs that you may already know what some of these pieces do. So what I want for you to do here is to think about what your guesses are for what h does, what k does, what a does, and what the sign on the a does. So it being positive versus it being negative. Do not leave these blank. If you want full credit, tomorrow when I check this, you need to fill these in. And again, refer back to our previous parent graphs if you want, and guess that they might do something similar. So fill in your guesses for all 4 of those. The only variable that is a new concept is b, which is why I didn't have you guess here, because we don't have any previous experience with b. Now, in order to complete this, you need your graphing calculators. So if you don't have it with you, pause this and get it, because you need to actually graph these in your graphing calculator if you want to know what you are doing. So for example 1, it says graph the following functions on the same coordinate grid on your graphing calculator. So that means what you're doing is you're going to your y equals screen, and in your y1, you're going to type in 1 times 2. Your exponent button, remember, looks like this. It's a little caret. So you'll press the caret button and then put in x. So that should be your y1. So I'm going to go ahead and graph that one first. And remember that you can do second graph shows you the table. And that can be immensely helpful when you are plotting these points because it gives you a t-chart. So the first couple are very easy to plot. You'll see, and I'm sure it pops out to most of you, that you have the point 0, 1, and you have the point 1, 2, and you have the point 2, 4. So those ones are relatively easy to graph, but you can't stop there. You need to keep going on the other side. There's lots of other values over here, regardless of how small they may be. So even though they are fractional, you need to plug them in. 2 to the negative first is 1/2. So this -1 is 1/2. Now again, I want you to see this relationship. Yes, I can look at the table, but if I'm graphing this by hand and I were making a t-chart, again, what I would be doing is just picking values of x. So let's say I picked these values. So we've already got 0, 1. We've got -1, 1/2. We've got 1, 2, and 2, 4. 3, if I plug it in, would be 8. That's off my graph, which is why it's not plotted. -2, I want you to see what we'd be doing here. We're just plugging it in here. 1 times 2 to the -2nd, which would be 1 times anything is just 1, so we've just got 2 to the -2nd. So 1 over 2 to the 2nd, which is 1/4. So that would be the y value when x is -2. So -2, 1/4. You can imagine -3, that'd be 2 to the -3rd, which is 1/8. So again, very small, but it's just above 0. When I draw this graph, my asymptote, the line that it is approaching, happens to be my x-axis, or the line y equals 0. It's getting closer and closer and closer, but it's never crossing it. If you scroll in your table and you keep going and going and going, it never actually crosses below that axis. It stays above it, gets closer and closer and closer, but never crosses it. So my asymptote here is the line y equals 0, or the x-axis. All right, so now let's graph my other ones here. So in your y2, you're going to type in, of course, not the f of x part, because that is y. You're going to punch in 4 times 2 raised to the x power. And you can keep the other one there if you want to compare them side by side, but you can look at the table, and again, you're looking at the y2 column of your table, and you can see that when x is 0, y is 4. So that's this point right here. When x is 1, 4 times 2 is 8. So that's off my graph. When x is -1, 2 to the -1st is 1/2, and 4 times 1/2 is 2. So it goes there. Then when I've got -2, it becomes 1. At -3, it becomes 1/2. And so I have the same asymptote. It's still approaching that x-axis, but it looks a little different here. Now let's look at the third one. I graph the third one. Please remember, when you actually type this into your y3, you need, unless you have the newest version of the calculator that actually shows you a fraction that looks like this, if you have an older one, remember that that 1/3 needs to go in parentheses. So type it in like this if you have the older version of the calculator. All right, and then when I do that, most of these come out fractionally. So when x is 0, I've got 1/3, so 0, 1/3. It's right there. When x is 1, I've got 1/3 times 2, which is 2/3. So right here. When x is 2, I have 4/3. And when x is 3, I have 8/3. And 8/3 is 2 2/3. So it looks about right here. Then on the negative version, look what happens. When my x is negative, 1/3 times 2 to the negative first, that's 1/3 times 1/2. So that's 1/6. So really, really little. But again, notice if you look at the chart, it never crosses that axis. It has the same asymptote of the x-axis. So, looking at our graphs, the original a was 1, just like it would be on a parent graph. My y2, I made it bigger. I made the magnitude of a bigger than 1. And what happened to my graph was that it shrunk up. We compressed it. When the magnitude of a is between 0 and 1, so like this 1/3 here, which would be this graph, I took my original parent graph, the number 1, and it kind of enlarged it or stretched it. So that is the effect that the A has. So wider, narrower, kind of isn't the right expression when we're talking about an exponential. So that's why I say shrinks and enlarge, but it's the same concept. It controls how wide the exponential is going to be. So when a is bigger than 1, you're going to have the graph that's compressed. It shrinks up. When a is between 0 and 1, when it's a fraction, it's going to stretch out or become enlarged. Example 2, graph the functions on the same coordinate grid on your graphing calculator. So same thing. Notice the number 1 is the same, so don't retype it. Look at number 2. The only thing that I've changed here are the signs. So save yourself some time. Keep the ones that you already have in your graphing calculator and just change the signs on 2 and 3. 1 is exactly the same, so I'm going to graph it exactly the same way I did before. Maybe I'll even use the same color. So when I graph my original number 1 here, I'm going to have the same points I did the first time. I've got 0, 1, negative 1, 1/2, negative 2, 1/4, 1, 2, and 2, 4. So here's my original exponential. Again, it's got an asymptote of the x-axis. So this is number 1. Number 2 now, that I made it negative. Again, you can follow it in your t-chart to plot it. You can make your own t-chart if you want. I just plug in numbers really quickly. When x is 0, 2 to the 0 is 1, so that's negative 4. So 0, negative 4. When x is 1, negative 4 times 2 is negative 8, so that's off the graph. When 2 is negative 1, negative 4 times 2 to the negative first is negative 4 times 1/2. So that's negative 2. So that goes here. And then when I have negative 2, 2 to the negative 2 is 1/4. Negative 4 times 1/4 is negative 1. And you can see that it follows the same pattern as what I had in example 1. It has the same asymptote, but the only thing that has happened, if I look here, from what I had in 2 to now what I have in 2 on example 2, all the points, if you'll notice, are reflected over the x-axis. They're flipped upside down. Let's test this hypothesis by looking at number 3. Again, The only change from the number 3 in example 1 is that now it's negative. So look at your chart to plot it or do it by hand. When x is 0, I've got negative 1/3. So right here, when x is 1, I've got negative 2/3. When x is 2, I've got negative 4/3. When x is 3, negative 8/3. When x is negative 1, I have negative 1/6, and so on. So my hypothesis seems to be holding true. The only difference between number 3 in purple here and number 3 in purple here is that all of my points are flipped upside down. It's reflected in the x-axis. And that seems to be what the A has always controlled, whether it goes up or whether it goes down. So if the sign of A is positive, then the graph increases. If the sign of A is negative, it's going to be reflected or flipped, and therefore it decreases. It's going down to negative infinity. All right, last one for now. So I've got 2 to the x, which again, notice is exactly the same as 1 times 2 to the x. So I'm keeping my first one the same as on all the other ones. So I've got the same points, 0, 1, 1, 2, 2, 4, negative 1, 1/2, so on and so forth. So here's my first graph for number 1. Now I'm looking at what h is going to do. And notice these are the same. They're not the same as what I had in example 2 and example 1, but they are the same. This is my parent. Number 1 is my parent graph. And these are the changes that h can make. So now you're going to have to clear out your y2 and your y3. We're going to have to redo those. Now, be careful. If you have an older calculator, when you press this into your y2, you need to press it in like this, 2, and then caret button, parentheses, x minus 4, because you need to tell the calculator that this whole thing is the exponent. If you don't put it in parentheses, it's going to graph the wrong thing. Now, if you have a newer calculator that actually puts this x minus 4 up higher in an exponent, obviously you can see if it's in the exponent or not, and you're fine. But if you have the older one, you have to use parentheses. So when I do that, what I see when x is 0, y, where'd I go? I just was looking at the wrong one and got myself confused, sorry. When x is 0, I have 2 to the negative 4th, which 2 to the negative 4th is 1 over 16. That's very, very tiny, small right here. When x is 1, 2 to the 1 minus 4, that's 2 to the negative 3rd, that's 1/8. Again, still very, very tiny. When x is 2, that's 2 to the negative 2nd, 1/4. Again, very small. When x is 3, 2 to the negative 1 is negative 1/2. When x is 4, I finally got 2 to the 0, which is 1. When x is 5, 2 to the 1st, and finally it becomes up to 2. When x is 6, 6 minus 4 is 2, 2 squared is 4. So there it goes. So very, very small. Notice I still have the same asymptote. Now let's look at what happens with number 3. Again, when you punch it in, if you have the older version of the calculator, you should be pressing this with parentheses. So I'm just going to plug it in by hand. When x is 0, 0 plus 2 is 2, so 2 to the 2nd is 4. So 0, 4. When it's 1, 2 to the third is 8. That's already off the graph. So negative 1. Negative 1 plus 2 is 1. So that gives me 2. Negative 2 plus 2 is 0. So 2 to the 0 is 1. Negative 3, if x is negative 3 plus 2 is negative 1. 2 to the negative first is 1/2. So here is my graph. Notice that they have all these points that line up on the y values. The only thing that's happened is I have shifted the graph. I've taken my red graph and here I moved it to the right 1, 2, 3, 4. And look at that number, right 4. If h is subtracted, then the graph moves to the right, just like we've always done. H has always controlled the horizontal shift, so it shifts right. Then here, the plus 2, if h is added, then the graph shifts to the left. All right, that is all for your introduction. The rest of your packet we're going to be doing as your classwork tomorrow. Again, make sure that you did not leave those 4 blanks blank. Make sure you filled these guys in at the beginning. That is all for today.